Hey, this is Barack Lemires. In this video, we're going to look at the relationship of pointers and the array in C. All right, so we have looked at how you can define a variable and it'll have a label, okay? And so, for example, A is equal to 22. What that does is it puts a piece of information into memory. It allocates memory. It allocates 32 bits because it's a type int. It gives it a reference and it gives the information in. It puts it into memory. Okay. Then this is called a scalar, right? So it's a scalar that you can just use it directly. You can reference it directly. And then we learned about pointers where you could reference it indirectly. Then we looked at arrays. Okay. And arrays was where you had a name, but then you had a dimension and then you had information that could be put in there. And so in this situation, if I initialize this to have 5 ints of these values, you'd have A and then you'd have an associated index. Notice that A, you never really use it alone. It has to have an index, okay? However, A is actually a pointer to the first address in the array. So that's what A is, okay? Now the index is the starting address plus a particular index to get to the next location. That is why it's so important to give the data type when you set up the array, because even though I can access these elements just by going 0, 1, 2, 3, 4 as indices, that 0 and 1 and 2 and 3, 4, that has to know how far away the next element is. So in this situation where this is going to be an integer, the next element is 4 away. So it's address 04, 08, 0C, 10, 14. But if these would have been integers, so simply changing that to integer, this would have then changed these addresses to be 8 addresses apart because these would be a 64-bit field. And so it's very important. So the data type is very important for indexing. And what arrays do is they give us a very easy way to handle that, okay? But A itself is actually a pointer to the first address in memory, okay? I can even assign A to a pointer. Okay, I can initialize a pointer using A without the square brackets. Think about that. That's the only time you can ever do this. All right. A is nothing more than the address of the first element. Okay, so they're the same thing. Okay. All right, so let's code along and just take an example of this. So I'm already logged into the Linux server. Let me change into my mod 09 code along directory and let me vim a file called pointers and arrays.c, and we're just going to play around with testing this. Okay, so let me do a comment header, pointers and arrays, and then what I'm going to do is bring in the standard io.h library. Then let's set up our main function. So int main void, open curly, come down here, return 0, close curly, and there we go. Now we're ready to roll. So let's come up here and let's do this. Let me set up an integer I, okay, just in case we want a looper. Okay, so I'm going to go int and then I. All right, and then what we're going to do is I'm going to do an example of this. I'm going to say int, and then I'm going to say A, that has 5 elements in it, and I'm going to initialize it with these integers, 77, 56, 28, 99, 109, okay? And then I'm going to create a pointer, which I'm going to call A pointer. Now this is a pointer variable, because I use the asterisk when defining it, that said this name is going to hold an address. This is a pointer that I can assign to. And I'm going to go ahead and just assign that. Notice I didn't even need to put like ampersand on it. I didn't even need to do that. Okay, so now let's print these and see what I get here. So I go printf, and I'm going to do this. I'm going to see if the address of A0, element A0, is the same as the pointer. So let me do this. I'm just proving this to myself. I'm going to go ampersand A of 0 address equals, and then I'm going to print the pointer address using the format specifier %p, and I'll return it, and then I'm going to actually put into the pointer variable the address of A element 0. Okay, and then I'm going to make this a little wider. Okay, and then what I'm going to do is right after it, I'm going to printf a pointer address equals, and I'll do the pointer format specifier, and I'm going to print the address of what where this is. So a pointer. So what's being held in a pointer? These both should return the exact same thing. Okay, and that'll prove that this is true. So I'm going to change my mod 09, and then I'm going to go ls, what's in here? Okay, GCC. I'm going to do pointers and arrays. Direct the output to pointers and arrays. Without that, I go, pointers and arrays, and I run it, and lo and behold, it's the same. Okay, so it's like, okay, what did I prove to myself? I proved that an array name is a pointer. That's what I was able to prove right here. Okay, that's what I ended up proving to myself. Okay, now let's see if we can access information within an array using the pointer syntax. Okay, so now here's what I'm going to do. This is why I made this I variable. So I'm going to go printf, and I'm going to say accessing a using array name. Okay, and now watch what I'm going to do. I'm going to go for loop, I is equal to 0, I is less than the dimension of the array, and then I plus plus. Okay, open curly, and I'm going to say printf, and what I'm going to do is I'm going to say a at the index, a at the index I. Okay, I'm going to actually print I there. And then I'm going to say this equals, and I'm going to print the value in the array. And I'm going to do this just like we have in the past. So nothing is new right here. Okay, I'll print I in this location where that format specifier is that I'll fix in a second. And then I'll print A at I at this location. So this is how we've been doing it. Okay, so close the curly, life is good. Let me go up here, and let me do this. And I'm going to say, yep, you are right. Okay, you are almost right. Let me pull this over here and fix this typo. So what I'm going to do at this point is I'm good to go. And now I'm going to come down here and I will run this little fella. So let me go ahead and GCC it and then run it. And I printed them all out. Why did I do that? Because what I'm trying to do is show that this is equivalent. So now what I'm going to do is I'm going to copy this entire thing. So I'm going to go into visual mode. And then I'm going to go down, 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 hit the Y button to yank it, and then I'm going to hit the P button to print it. And now what I'm going to do is instead of doing it with the array name, I'm going to do it with pointers. Okay? And I'm going to do the same looping structure. I'm going to print the same thing here. Everything's exactly the same, but watch what I do now. I am going to do the following. I am going to do value of a pointer. And if I think about that, it's like, okay, what will that do? That will print the value held in a pointer, but that's just the first address. How in the world am I going to cycle through these? I can actually use plus I, the index in my for loop, to go to the next element. Okay, now let's check that this works, and then let's unpack what is going on. All right, so we go like that. Oh my gosh, it worked. Okay, it did work. How did it know that I needed to increment 4 addresses? It knew it because a pointer was pointing to a type integer. So the compiler, when it compiles this and looks at this loop, it knows that that I is going to increment addresses by 4. Okay, so this is awesome. We can access arrays with pointers. We can do it with arrays. Life is good. Okay, now here's the question. Take a deep breath. Why are we doing this? Okay, why are we doing pointers? We already have a way to address arrays, and it works very simple. Okay, pointers seem less intuitive than arrays. I mean, to be honest with you, I like the square brackets. So here is why. There's 3 real reasons. The first is to pass a parameter to a function by reference. Okay, and to understand what that means, we got to look at how information is passed to a subroutine or a function. Okay. So let's go back to our memory map of a computer, okay? You've got your program memory where your executables go, you've got your data memory where variables go, and you've got your input-output, okay, or your keyboard and your display. If you look deeper into memory, variables are given a dedicated address in memory, okay? So if I look at A, it's basically like it's assigned to these addresses up here. But there's another part of memory that's a temporary storage that's used to dynamically store stuff and then disappear or destroy it is what they call it, okay? The temporary storage in a computer is implemented as what we call a stack data structure. A stack is a last in, first out system, okay, LIFO, and it's very analogous to a stack of plates, okay? So you basically, if you had a plate, stack 4 plates, 1, 2, 3, 4, notice that you can only take plate 4 off first. So you can't get to plate 1 unless you unplate the rest or take off the plate. We call it pushing to put information on the stack, and we call it popping to get it off. So pop, 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 pop. That's the way memory works when you need temporary storage. Now, let's go into the details of the stack so you understand it just a little bit. The stack is a dedicated part of memory, of data memory, and there's actually a stack pointer, which is a register in the CPU that tracks the address of where you're pushing and popping information from. Okay, so this is built into the hardware. And if you wanted to get into gory details, you can think about it like this. Let's say that your stack started at address 3000. You'd point your stack pointer to 3000 hex. Then let's say you wanted to push AAA onto the stack. You would decrement the program or the stack pointer, put it on there, and then the stack pointer is now pointing to where that information was. And then if you wanted to push more information on, you could then decrement the program counter and then push more information on. Notice that the stack or pointer is holding the address of where the last piece of information was pushed. Then if we want to pull it off, what you can do is say, okay, go ahead and read the information from where the stack pointer is pointing. And then all we have to do is increment the stack pointer down, and it's now pointing to the next location. And if we want to get that, which in this case would be AAA, we could then go grab that, and then the stack pointer is incremented. So basically what a stack pointer is in physical hardware is an address pointer in the CPU that moves up and down in the memory space, and it pushes or stores information in based on the address it's at, and it pops it or reads it out based on where it is. So this is built into the CPU. Now here's what's cool about it. You don't need to keep track of it. And oftentimes you can be a computer programmer without even knowing a stack exists. It's all abstracted from you. Okay. So this is a good thing. But it helps us explain how you pass information by reference. So let's look at actually what happens when I call a function. Okay. Let's say, for example, I had 2 variables, var1 and var_sum, and I'm going to add them together, or excuse me, var1, var2, and I'm going to add them together into var_sum, and I want to store that. And I create a little function that is going to be called g, and it's going to I'm going to pass var1 and var2 to it, and then I'm going to return it to var_sum. Okay, so this is a subroutine, or excuse me, a function that's going to happen. So here's what happens. When you call the function, the values you pass in the parameter list are copied into the stack. So copies of them are made. It is not the original information, it is copies. Then what happens is it goes down and runs the code, runs the instructions associated with the subroutine, G, okay? And then what happens is the result of those instructions are then pushed back onto the stack. Notice that the stack can just keep cranking these things up. And when you return it, what happens is that the return variable is then copied off the stack back into the memory location that you wanted. In this situation, var_sum. So it came from the stack and then it ultimately went into var_sum when everything's over, okay? Then all the data that was pushed onto the stack is essentially destroyed. Destroyed just means the stack pointer goes back to its original location. So it's no longer available. All right. That is why you can't alter the input arguments in a function. They're only temporary copies. The only way to get information back is by returning it, and return is a special command that actually moves information from the stack back into your memory. Okay. Even if as a function you were messing around with the input values, they would be destroyed as soon as the function ends. Okay. So that's interesting. So now you go, well, what if I wanted to physically change the information that's up in my dedicated memory space? Well, you guessed it, pointers. That's the whole lecture. So this video is about, of course, it's going to be about pointers. So now let's think about this. What does it mean to use pointers? Instead of passing the copies of the value, what you can do is pass a copy of the physical address of where they're at. So for example, let's say that I have a subroutine. I'm going to pass it a pointer. So I'm going to pass it a pointer, and that pointer just happens to be the location of where memory is, or where the values are in memory. And then what happens is Your function can then use that to go up here and directly access your memory. That is called passing a parameter by reference, okay? Because you didn't send it the information directly, you sent it an address of where it's at. So it's called passing a parameter by reference. But both the caller and the callee use the same information at the physical address of where it is in memory. Okay. This works great for arrays because if you're going to alter something in an array, you don't want to copy everything onto the stack. These arrays can be huge. Imagine like an array that holds like a song. It's going to be megabytes long. You don't want to copy that over. You also don't want to pass the address of each piece of information in there because that's equally as long. But you do want to pass the starting address of it and then allow the computer program to use offsets to access the information. Okay, so this works fantastic for arrays. That was a long explanation. You probably could get through being a programmer without that, but you're way better if you understand it. Okay. Now, another reason pointers are great is because you can allocate dynamic memory. So imagine that you set a pointer into a address in memory and then say, I'm going to allow you to put a bunch of information on there. Like let's say scanf was in a loop and you just go, oh, I'm just going to scanf in this location. Then I'll go to the next, and I'll go to the next, and I'll go to the next, go to the next. The only way you can really do that is with a pointer to the start of your block of memory and indexing. Okay. And then it's also good for complex structures, which we're not going to cover in this video. You can have pointers to pointers. You can have arrays of pointers. And this allows you to do all sorts of really wacky data structures that are awesome and are beyond the scope of this video. Okay, that is pointers and arrays and why they are so interlinked and why it's so important to have pointers to be able to pass information by reference to a function. And see ya.